Hi, my name is Muhammad Arif bin ALZARI and my partner Lim Junpin from Group 24. In this video, I will show you about active filter circuit simulation using multisim. For the first circuit, it was a first order low pass filter. As you can see here, I have already constructed the circuit with a cut-off frequency of 159.15 kHz. As the question that is given in the lab sheet, I have to set the input frequency from the minimum 1 kHz to the maximum 1 MHz with 1 VRMS. The output voltage for 1 kHz is 1.5 volt. When I set the input frequency 1 MHz, it will become 117.85 millivolt. So, the higher the input frequency, the lower the output voltage will produce. Thus, the active low-pass filter has a constant gain F from 0 Hz to the high frequency cut-off point. At the cut-off frequency, the gain is 0.707 DC gain, and after cut-off, it decreases at the constant rate as the frequency increases. That is when the frequency is increased 1 decade, the voltage gain is divided by 10. In other words, the gain decreases 20 dB each time the frequency is increased by 10. Lastly, I will show you the bot plot output. This is the first order low pass filter bot plot. Next, I will show you the first order high pass filter circuit. As the question that is given in the lab sheet, I have to set the input frequency from 1 kHz to 10 kHz with 1 volt VRMS. The output voltage for 1 kHz input is 800.442 millivolt. But when we increase the input frequency to 10 kHz, it will become it will increase to 1.485 volt. The result is vice versa to the low pass filter. It means the output voltage will increase when the input frequency increase. In the stop band from 1 kHz to 10 kHz, the gain increase at a rate of 20 dB per decade. However, in the pass band after the cut-off frequency 1 kHz, the gain remains constant at 3 dB. The upper frequency limit of the pass band is determined by the open loop bandwidth of the operational amplifier used. Then the plot of the filter circuit will look like this. This is the bot plot for the first order high pass filter. For the last task, the question asked me to find critical frequency, passband gain, and the damping factor for the second order low pass filter. By using the formula, I get the critical frequency 5.305 kHz, the passband gain 1.667 dB, and the damping factor 0.667. Then the baud plot of the filter circuit will look like this. Higher frequency are attenuated more severely by the second order filter. The baud plot of this type of filter is similar to that of first order filter, except its fall off faster. Per time the frequency doubles, a second order Butterworth filter reduces the signal amplitude to 1/4 of its original level, resulting in a power decrease of 40 dB every decade. As a result, the simulation cut-off frequency is 6.15 kHz. This number has been normalized based on the compute value. The cut-off frequency is 5.305 kHz. This is because the compute value has been normalized. The damping factor in the active second order filter is often the inverse of the quality factor. According to the data analysis, the damping factor is 0.667 and the quality factor is 0.75. To summarize, when the quality factor value decreases, the damping factor value increases. This second order low pass filter has a gain of 1.667. This is all from me, and thank you.